Hello guys, how are you doing today? Hope your day is good and cool. Yeah, for today's lesson, we're going to look at Earth and beyond. All right, it's a checkpoint uh, topic, and it's one of the lessons we're expected to learn by checkpoint exams. And we are going to critically look at the night sky, what we can see in the night sky when you move outside at night, and we will proceed to day and night, and then to stars, and then the solar system. And from there, we're going to move to the moon, study the different phases of the moon, and there we'll be able to find out why we have the different eclipse of the moon or the lunar eclipse, solar eclipse, and so on. Then we're going to briefly look at tide, and then move to um, beyond our solar system, what we can see beyond our solar system. But before we look at what we can, what we see beyond the solar system, we look at around the solar system, other items like the different uh, regions that we have in our solar system, like the asteroid belt, the Kuiper belt, the Oort cloud, and what we can actually find in some of these belts, right? And we are going to briefly look at satellite, the different type of satellite, and what it does also. Okay, so let's quickly move to the first model of what we have today, the night sky. Now, one of the things we see when we move outside at night is the star. And a star is actually a luminous object, a luminous body. It gives out its own light, okay, continuously. Now, later on, you're going to briefly look at how and why it gives out its own light, okay? Now, the closest star to us is the sun, which is about 6,000 degrees Celsius or centigrade, as the case may be. And we have other stars like the white colored star, which is about 11,000 degree, the blue colored star, which is 25,000 degree, and the orange colored star, 4,000 degree, and the red colored star, which is 3,000 degree. Okay, the moon is another thing we see when you move out, sometimes in the night sky. I believe we can all identify the moon when we see one. Okay, it is not a planet. Okay, even though it looks spherical when we see it up there, it is the closest object. Okay, not man-made, but natural object to the Earth. Now, for this reason, it is called a satellite. Okay, later we are going to look at the different types of satellite. The natural one, which is the moon, and the artificial one, which are man-made. All right. Now we are also going to look at the different types of artificial satellites. Okay, that is as we proceed in the lesson. A comet is another object we can find in the night sky. All right. The comet is made up of ice and dust. or organic matter. It orbits the sun. It orbits the sun, and as they get closer to the sun, it produces something like a tail. All right. We sometimes see comets in the night sky. It's not often, but sometimes, if you're lucky, you find something like that similar in the night sky. Okay. Another object we see in the night sky is a planet. On a very good, bright night, you may be fortunate to see planets that are Venus, there is Jupiter, Mercury, and so on that you can actually that are visible in the night sky. So objects called planets made up of rock and gases are actually what we call planets. So some of these planets can actually be they are visible in the night sky. You may sometimes assume them to be stars, okay? Except you're using the telescope. You may assume them to be stars because you see them reflecting, giving out light. Okay? But you can actually identify that this is a planet if the light that comes from it seems to be much more brighter and closer, right? Now they do not give out light on their own, like the sun. So they are actually referred to as non-luminous objects. The brightest planet seen in the night sky is actually Venus, which is called morning or evening star. Some planets, however, cannot be seen with the naked eye because of their distance from us. Okay, some of the examples are actually stated there. The Uranus that you see here and the Neptune. Okay, these ones cannot be seen. Now, another object you may be fortunate to see in the night sky is a meteor. Now, meteor is actually a piece of rock that enters the Earth atmosphere and burns up. We sometimes call it a shooting star. Okay, they are debris, rock debris, probably from the asteroid belt. Okay, that lost its way, that loses its orbit. Okay, then move directly to Earth's atmosphere. Now, sometimes these meteors are large enough, okay, to pass the different phases as they move from space to Earth and land on the ground. Okay, whenever it touches the Earth, the remaining parts we call it a meteorite. So a meteor is a piece of rock that enters the Earth atmosphere and burns up. Burns up due to friction between the rock or the substance and the atmosphere, okay, as it's moving. So the friction generates a lot of heat, which causes burning. So meteorite is a piece of rock that survives the burning and reach the ground. They occasionally appear in the night sky. Other objects found in the night skies are man-made satellites and international space stations. Okay, now we see planets and the moon because they reflect light. Now look at the picture diagram below, diagram on your screen. You see the sun, the the moon actually reflecting light from the sun to the astronaut's eye, right? So that's why we see the moon, okay? Because it actually reflects the light coming from the sun. Now, can you identify some of these things you see on the screen? Can we identify it? Now, this one is a moon, and this is a comet because of the tail. Remember, I said the comet sometimes produces a very long tail. I'm going to tell you why shortly, okay? Why it does that. it's actually made up of gas and organic matter or dust. Okay, the gas can be vaporized water actually. Okay, water that is being vaporized as it moves. Now look at this. What do you see? What do you observe? Venus very close to the moon, right? Very bright. Jupiter and the different constellation pattern of different constellation of the stars, right? And this one, they are all shooting stars, right? They're actually meteor falling down. In this case, we call it a meteor shower. Tiny debris, rock particles falling down, and as a result, they are burning off because of friction between the atmosphere and the rock. Now, what do you see in this picture? Why is the tail? What is the tail made up of? In which direction can we find the sun if you look at this? Now, in the picture here, we see this. This is actually a comet. Okay. Now, did you notice that the Earth is the tail is like a vapor? You see, notice that it's like a vapor. It's actually vaporized ice and dust particles. Okay, as it moves. Now, for the direction of the sun, for the fact that the vapor is here, it means the solar wind is coming from this side, from the right hand side. Okay, from the side. That means the sun must be here. Okay. Now look at this picture closely. You will notice the comet moving around the sun in an elliptical orbit or oval orbit. Did you notice it? Now you see as it gets approaches the sun, what happened? It releases some gases, right, in form of the tail. That is the tail we see when we look at it in the night sky. Now you notice that it releases the gases when it's closer to the sun. Okay, this is actually caused by the flares of the sun or solar wind, right? So it is driving it away from the sun. Okay, so the gases are dust and moisture, water particles that are contained in the organic matter or rock sometimes. Okay. We have these. Because of these, how do we have these? What is actually the cause of night and day? Okay, the cause of night and day is simply due to the rotation of the Earth around its axis. Okay, it's like you're on a spot and you're spinning round and round that spot. Okay, so the Earth is actually spinning, going round and round, and it takes 24 hours for a complete rotation around its axis. Okay, the Earth rotates in an anti-clockwise direction. That means it moves from the west towards the east. So that's why it appears as if the sun rises from the east. Notice that if you're on the car and you're driving from the west to the east, a tree by the side will appear to be rushing towards you, right? If you're on the car, you're moving from west to the east, the tree will appear to be moving towards you from the east. So that's exactly what's happening in this case. As the earth rotates from west to east, the sun appears to come from the east. Okay, so we see the sun rising from the east and setting in the west. Look at this diagram. This will show you what is actually happening. This is a straight line, imaginary, that represent the axis of the Earth. Okay, it's a North Pole, and here is the South Pole. Okay, and the Earth is spinning west to east continuously, right? And for one complete spin, we have 24 hours. It takes 24 hours. Okay, and that's exactly what gives us the day and night that we have. Half of the 24 hours is our daytime, and the other half is when we have the darkness, which we call the night time. Okay, and one other thing, notice that the Earth is not like perfectly vertical. It's like it's slanted. It's tilted, right, by the side towards the right, slightly. So the Earth is actually tilted. In space, from a proper observation, you notice that the Earth is actually tilted, not straight. Okay. Now later on, we are going to see the result of this tilt. Okay, what it actually costs. Days and years. How long does it take for the Earth to spin once in its axis? I believe you know the answer, right? We've said it before. For the Earth to spin around its axis, it takes just 24 hours. How do the Earth and the Sun move in relation to each other? Okay, while the Earth spins around its axis, it also moves around the Sun, the orbit. Okay, it also orbits around the Sun, and it moves around, revolves around the Sun. Okay, now let's look at this briefly to see exactly what is happening. Can you see this? It takes 24 hours to complete rotation. Okay, and the Earth is tilted at this angle, 23.5 degree to the horizontal. If this is a horizontal line, if you measure it to the horizontal, it's going to be, you're going to get 23.5 degree. Okay, and now let's look at how the day and night is formed. Look at it on the screen. If you see the screen here, you notice that part of the Earth, if you cut it into two hemispheres, one part of it is bright and the other part is dark. The part that is bright is actually daytime, while the other side is nighttime as it spins. Notice Australia is going to move to the other side, right? Look at it. Now, this is how the Earth moves in relation to the Sun. It moves around the Sun. It orbits the Sun, or we can say it revolves around the Sun, right? And this one brings about the years, a year. Okay, one complete orbit or one complete revolution. It takes about 365 and a quarter days. Okay, now this is a sample of day and night. The sun is actually from this side, so this side is the day side, while the other side, where the sun cannot get to, is on the night side. So it takes 24 hours. We've said it before. This will give us a clear picture with the sun, the earth, and the axis of the earth, how it's tilted. Now, while the earth is spinning, the side that faces the sun is in what? It's in daytime, right? Okay. How long is one day? A complete day is about 24 hours, and 1 year is about 365 and a quarter day. Okay, we've answered this question. Now, I told you uh, uh, previously that the tilt of the earth actually does something. Okay, the tilt of the Earth results to something, especially when it's moving around the sun, when the Earth is moving around the sun. So one of the consequences is this season. Okay, one of the consequences is the different season that we have. We're going to see it in a short while. Now, the path that the sun takes. Now, let's quickly go through this and look at the path that the sun takes. When you observe, the sun will appear to move from east to the west. Now, this animation is from a view of someone living in the northern hemisphere and observing, looking south. So the sun will appear to come from here and set here. Okay, that's during the summer. But during the autumn or spring, the sun will also appear to come from east to set west. But this time around, it will appear to be closer to the earth. Okay, I'm going to tell you the reason in a short while why the sun appeared to be closer to the earth during the autumn and spring. And then for winter, the guy observes that the sun is even much more closer to the earth compared to other seasons. Did you notice it? Rising from the east and setting in the west, but much more closer. You're going to get all these, some of these reasons shortly as we proceed. Now, the hemispheres. The earth is actually divided into hemispheres. If you are to divide the earth into two parts, perfectly two parts. Maybe you have a sphere like a ball and you're asked to cut it into two parts, and you happen to divide it from the middle. That point where you cut it, that point where you actually cut it is the equator. Okay, so this point here is the equator. The middle here, where you actually cut it, is the equator. Okay, so that's the equator there. All right, so this point here can be called the equator. Right, if it's the earth that you are to split into two parts. Now, the top part is the northern hemisphere because it lies in the north, towards the North Pole. So this part can be called here, can be called the northern hemisphere. Okay, while the bottom part is called the southern hemisphere because it falls at the South Pole, towards the South Pole. Okay, all right. So this is the northern hemisphere, the southern hemisphere, and the equator, the point where it's split. It's cut into two. All right. Okay, so we have the north, like I said, the north, the equator, and the southern hemisphere. So why do the hemisphere have different seasons at different times of the year? Like if you're in the northern hemisphere and your friend is living in the southern hemisphere, somewhere in the southern hemisphere, while you're in summer, experiencing summer, your friend may be experiencing winter. Why is that so? Okay, we're going to find out shortly why the hemispheres experience different seasons. Now, let's look at this picture. This GIF animated picture here. Now, if you look at this, the Earth is actually tilted, right? It's moving around and around, day, night, day, night, day, night, day, night. Now, if I should divide this into two parts, I should divide it into two parts. I should cut this into two parts from the middle. You notice something, that the sun gets to the south more than the north, isn't it? Okay, so because the sun gets to the south more than the north, the south will be in summer. Since the south gets more of the sunlight, it will be in summer. Did you get it? But the north that gets less of the sunlight will actually be in winter, right? Because it's not getting as much sunlight as the south, right? Okay. Now look at what will happen when it moves. When it moves, look at how it's going to move. The winter and the summer for the first quarter. Okay, like you're moving round and round. So for the first 90-degree or for the first quarter, as the case may be. Now, for the first quarter, notice that none is actually facing the north and the south. None is particularly more to the sun than the other. They are facing the sun uh, the same ratio, if I may put it that way, or they're getting the sunlight in the same manner. All right. Okay. But then there's something different. The Earth is still tilted, isn't it? The Earth is still bent. So it's tilted towards the left, right? Okay. And the distance from this to the sun is not the same thing as the distance when it was at the starting point here. Okay. Because the orbit is not perfectly circular. Okay. It's elliptical. Now, for this reason, the north here is going to be spring and the south will be autumn. And for the next quarter, that is next for the first 6 months or another 3 extra months after the first quarter. Okay, let me call it the second quarter. This time around, notice that the tilt, the Earth is still tilted, but the sun gets um, the northern hemisphere get more of the sunlight compared to the southern hemisphere compared to when it was here. Did you notice it? So if I should divide this into two, you notice that the north get more of the sunlight. So the north is going to automatically be in the summer period, while the south that doesn't get the sunlight will be the winter period. Okay? And then the last quarter, or the next quarter, if I may say, the next quarter, that is three-quarter rotation um, around the orbit, which is around the sun. Okay. Here, let me take it backward slightly. So this time around, it's similar to what happened here. Okay, it's similar to what happened in this case. Okay, it's similar. We have a similar scenario in the other case. But when it gets to that point, okay, the northern hemisphere, instead of spring, now will become autumn, while the southern hemisphere will have spring, and then back to where it started. That is the last quarter. Okay, and the cycle continue on and on and on. Okay, like take 365, it takes 365 days for this cycle, and then process continue. Okay, like from summer in the south to autumn in the south to winter in the south, and then to spring in the southern hemisphere, right? Or like from this winter in the north to spring in the north here to summer in the north, and then to autumn in the north, back to winter in the north. Okay, and the process continues. Now, why does the Earth have seasons? Now, this will give us a picture, a clear picture of why we have the summer in the south here. If I should divide it again, if I should split it into two parts to give us a clear picture of what is happening. If I should divide it, while we have the summer here and the winter here. Notice that the sun ray here is actually spread apart, spread out. But this one is concentrated, like it's hitting it at 90 degree, but this one is hitting it at a much more bigger angle. Okay, like it's spread apart, while this one is concentrated to this point. Okay, now imagine two identical sun rays hitting the Earth. Do the rays strike the same amount? Do the rays strike at the same amount in the Earth's surface? I think no. From the picture there, what effect do you think this will have on how the two rays hit the ground? Now, if you're to spread a ray on the ground, or you're to concentrate it at a particular point, what effect do you think it will have? I think this would cause more heating effect compared to this, right? Don't you think so? I think so. Now, look at this. Just an emphasis of what is actually happening. Summer in UK, and then autumn in UK, which is in the northern hemisphere, winter in UK at the third stage, and then spring in UK in the later stage. Now, this is also an emphasis to what we've learned earlier. Okay, but I wanted to notice something here. At the North Pole, we have 24 hours darkness. That is when it is summer in the southern hemisphere. At the North Pole, we have regions that will not experience a single ray of light. They will be in darkness for 24 hours. The same goes to the South Pole here. Okay. Now also notice that some here in the North Pole, the opposite will be the case. The reverse will be the case. To experience 24 hours daylight. Okay. That is during summer here in the North Pole. And while the South Pole, we have regions in the South Pole concentrated here in the South Pole here. Will have 24 hours darkness. Okay. Now there's no need to emphasize further. Let's just stick to what we need to know for now. Why is there more hours of daylight in summer? Why do you think we have more hours of daylight in summer than winter? Okay, don't worry, we're going to answer the question shortly. So a few slides, we're going to see the answer to the question. Now, the tilt of the Earth is the reason for the following. Number one, days are longer and warmer in summer, especially in countries at the pole. These are shorter during winter and cooler because of the tilt of the Earth. The sun is high in the sky in the summer than winter, and the different seasons are produced. Okay, this is actually caused by the tilt, the Earth being tilted. All right. Now, why do we have? Okay, we've looked at this previously. You just want to look at the formation of shadow and how it's formed. By 3 p.m., the shadow is going to be by the left. 9 a.m., the shadow is going to be by the right and longer. But noon is going to be shorter at neither right nor left. That is at middle when it's by noon time. We've looked at why this is what we expect, how they expect the shadow to be by winter. By winter, we expect a much more longer shadow compared to summer. And the noon time, we expect much more longer shadow that is neither to the right or to the left. Okay? By 3 p.m., a longer shadow to the left side. Now, this is the reason why we have the sun appear to be closer during winter and much more not too hot. Okay. Now during winter, the northern hemisphere lean away from the sun. Can I take you back? Show you some of the picture to see how the northern hemisphere lean away from the sun. Okay, let me use this as the northern hemisphere during winter. It's winter. This is the northern hemisphere here, leans away from the sun. It's not facing it's not tilted towards the sun. While the southern hemisphere leans towards the sun. All right. Now there are few leans away from the sun. There are fewer days, daylight hour, fewer daylight hour because of this. The sun hits at an angle that is not 90 degree, that it strikes at an angle. This makes it to appear lower in the sky. Now think of it. You're looking at something directly and you're looking at it at an angle. Okay? It's the illusion, okay? So when you're observing something at an angle, it appears to be closer. Especially if you're on a spherical Earth and you're looking at the sun at an angle, it will appear to be closer. Okay, now let me give you an idea. When the sun rises, does it appear to be closer or further away from you? Good, closer. It appears to be closer, right? When it rises from the east. This is because you're looking at it at an angle. But at noontime, when it's ahead of you, just directly above you, does it appear to be closer or further away? Of course, it appears to be further, right? Because you're not looking at it at an angle, you're looking at it straight, okay? Directly above you. But that's exactly what's happening in this case. So during winter, the rays come this way, so it appears to be closer. For this reason, since the ray is not concentrated, it's an angle, there is less heating, okay? Because of the angled sun rays are spread out, because the rays are actually spread out rather than being direct, okay? And then this causes shadow to be longer, okay? But during summer, the northern hemisphere leans towards the sun. in its revolution. So there are more daylight hours. You get more hours, more daytime hours. You have a longer day, as the case may be. The sun angle is more perpendicular to us, that is directly to us, or at 90 degrees, making it appear high in the sky. When are the other times of the year than the other times of the year? The longer days and more concentrated sunlight results in more heating effects. Okay, so shadow here are shorter in summer because the sun strikes the earth more directly. Okay, now let's go through this briefly and see how we can answer this. What is the season here in the northern hemisphere? The northern hemisphere, which one gets it's tilted towards the sun, of course, is the southern hemisphere. So the southern hemisphere is going to be it's going to be summer here, south. That means it's going to be winter in the north. Okay, so southern hemisphere, of course, is going to be summer. Remember the seasons. Remember the seasons, how it follows. After winter, we have what? Spring. After spring, we have summer. After summer, we have autumn. The cycle continues, right? Okay. So if we have if we have winter in the northern hemisphere, of course, in the southern hemisphere is going to be summer. If we have spring in the north, of course, in the south, it's going to be autumn. So they go hand in hand. Okay. For those of us that are going to try to mix it up. Stars. Now, in this section, we're going to look at stars, understand stars, and briefly look at constellation, and then move ahead. The stars. Now, we know that star is one of the objects we see in the night sky. That's when you go out. But many of us don't know that the sun is actually a star, the closest star to us. So the sun is actually a star, the one that is closer to the Earth. Other stars are millions of miles away from us. Okay, so other stars include Arcturus, which is 100,000 of times bigger than the Sun, Sirius, Polus, etc. So the brightness of the Sun prevents us from seeing other stars, especially during the day. So you can find other stars because our Sun is very bright, so bright that it prevents you from seeing. But if you're on the other side of the Earth, that is, you're in the night time, since the rays are not there to blind you from seeing the sun, the other stars, can you'll be able to see them. All right. So stars appear to move in circles in the night sky, not because they are moving, but because the Earth is actually rotating. The rotation of the Earth makes stars to appear to be moving. Stars don't actually move, but the Earth do. Now there are two stars that don't appear to move in the night sky. These are the Polaris, the northern pole star, and the Sigma Octantis, that is the southern pole star. They are used by sailors to navigate because of this property, this particular property. They don't move, so sailor can use them to determine where they are going. Okay, they don't change direction. But remember, stars don't move. It's the Earth that actually move, rotate. Constellation. Sometimes you look at the night sky, you notice that there are groups or clusters of stars forming different pattern. This pattern is actually called constellation. It's quite easy to describe stars. In fact, stars are described in constellation based on the patterns they form in the night sky. So different constellation is seen at the northern and southern hemisphere. That means if you're in the north, Myself in the northern hemisphere, I see a constellation pattern in the night different from what you see if you're in the southern hemisphere. Okay? Stars or star pattern seen by December are different from those seen in June. This is because the Earth orbits the Sun and it takes 6 months to be in the opposite side. Hence, the star we see the first 6 months are blocked by the Sun. That if you are uh, in June, for instance, it will take you 6 months to see another pattern, different pattern from the one you're seeing, or the one you see in June, July, August, September, October, November. This is because exactly 6 months you are in the opposite side, and the brightness of the sun prevents you from seeing the stars on the other side. Okay? Now let me use this. Let me explain. If you are in a room and you have a door, you cannot actually see what's happening on the other side. Let's say the sun is representing the door. You're in a room. You want to move out, but you can't see what's happening out there because the door is closed. Okay? Now, within the room, wherever you move, you can actually figure out the door, see the door. Okay, but the moment you move out of the door, you don't get to see what's happening in the room. That's how it is. So the first 6 months, you see whatever is within the region. That okay. The next 6 months, where you're being blocked by sun, you don't get to see what's happening there, right? You see only what's happening in the area where you are, the fresh area where you are. A group of stars forming a pattern that is traditionally named after its apparent form or identified with a mythological figure. For example, um, Orion. A group of stars forming a pattern that is traditionally named after its apparent form, like this. Can get the head in here. Now, this pattern can actually be named just to for easy identification anyway. So one of it is Orion. Others are this. We have so many others being named there. The origin of the sun or the life cycle of the sun, you can put it that way. The star, the life cycle of the star. All stars originate from clouds of dust and gas, which are commonly called nebulae. Okay, they abound in space. It's a process of nuclear fusion that powers a star for most of its life. Now, this it's a little bit advanced for checkpoint anyway to know all the explanation. But in your year E12, you get to see why or how a sun is formed. Okay, how gravity bring all the dust particles, the gases together and bind them together. How the binding force triggers what we call a fusion reaction, a nuclear fusion reaction, okay, which results to the production of all the energy and light the sun produces throughout its lifespan. Okay, the star first attain the stage of a red giant phase. In this stage, its core collapses into a dense white. Sorry, it attains this stage, the red giant phase, and then the core collapses to a dense white dwarf, which will soon expel what we call planetary nebula in its outer form. Now, this diagram explains it. We have A star can follow any of this depending on the size. Okay. Now this one is for the star of us of our own. The star whose size is similar to that of our sun. Okay, we can call it a dwarf star, and this is a massive star. Now, if you look at the life cycle of a dwarf star, it follows this pattern. Now, for massive star, it follows this pattern. First of all, from this stellar nebula collapsing on each other, and then which triggers a fusion reaction to take place. Okay, then we have our sun. Now, during the dying stage, this is a stable stage. This is the stage where we are right now, where our sun is right now. At the dying stage, it expands into what we call a red giant. All right, and afterward releases the matter that formed it. Okay, which is called this planetary nebula. All the matter that formed it together must have exhausted its energy, so it releases them and finally form uh, a core, which is called a white dwarf, a white core, which eventually fades out as a black dwarf or loses all of its light to become a black dwarf eventually. Now, for a massive star, we have the first stage, a massive star formed from stellar nebula, and then expands into what we call a red supergiant that is at the dying stage, and then releases or explodes. Okay, the explosion here we call it supernova, that is releasing all the matters that formed it, and then either become a neutron star or a black hole. Okay, so we can see that a black hole is as a result of um, a supernova from a red supergiant or a massive star. Okay, so that means our star cannot eventually form this. Rather, it will form this, a dwarf star. Okay, do we understand the steps or the cycle involved? Now, introducing the solar system. Introducing the solar system. The solar system is made up of various celestial objects. The word solar stands for um, sun. That means it's a system that revolves around the sun, that is being controlled by the sun. Okay, our sun. The solar system consists of these celestial objects or bodies. The sun, number one, which controls the solar system. Okay, the one that provides all the force, the gravitational force needed to hold every other object in place in our system. The planets, the moons, the asteroids, and the comet. How do these objects interact? How do they interact? We're going to see it shortly. Okay. The sun is a star that is a massive ball of hot glowing gas. It has the strongest gravitational field in the solar system. So that means all the other celestial bodies are being held by the sun. They are being forced to orbit, to move around, okay, or to fall around the sun, as the case may be. Now we can let's go back briefly. Okay, forward. We can remember the names of all the planets in our own solar system using this simple mnemonic here. My very educated mother just served us those. Okay, so the first letters are the ones we use: M, V, E, M, J, S, U, N. So M stands for Mercury, V for Venus, E for Earth, M for Mars, J for Jupiter, S for Saturn, U for Uranus, and um, N for Neptune. To remember the names in the order, okay? Now, some of you wonder why we don't have Pluto here, why we don't have this. I'll tell you the reason shortly, okay? Why we don't have Pluto, or why is Pluto not regarded as a planet? What are the names of this planet? One more time, let's go through it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Sorry, Pluto is not a planet, so let's leave it with a question mark. Okay, from here we can guess the closest planet, the Sun, the biggest planet, and we can even see the different belts. In one of the belts, here where we have the inner planets and the outer planets, right? Division there. Okay, next region, Kuiper belt, the other region, the Oort cloud. In 2006, the International Astronomical Union defined it as a planet as a celestial object that orbits the sun, has enough mass to be spherical, and has cleared the area around its orbit, okay, of any object. Now, this photograph here shows Pluto and its moon. Pluto actually orbit is actually surrounded by smaller objects, so it has not really cleared its orbit. We have a lot of dwarf planets around that region, so it has not cleared its orbit. Okay, so and Pluto also have a unique orbital pathway, okay, which is different from others, but that is not, anyway, that's not the reason why it's called dwarf planet. The reason why it's called a dwarf planet is because that's not fully cleared its path completely. It has other objects around, okay, like competing for space and all of that, though not closer. And the size, okay, so Pluto is a dwarf planet. Okay, but we are not going to look at the size only because we have Mercury, which is also smaller, but Mercury is a standalone object in that region, so it will be classified as a planet. Unlike Pluto, which is not a standalone object there. All right, do we understand why it's called a dwarf planet now? What other object exists in our solar system? Now, we have different objects that exist in our solar system. We have satellites, the man-made objects, space station. We have the asteroid. Asteroids are actually a large piece of rock that orbits around the sun. Now, if I take you back, you're going to see a region where we have a lot of them, piece of rock here. This region is actually called the asteroid belt between Mars and Jupiter. Okay. In 2006, okay, I've done this, we've moved ahead. They vary in size, but are considerably too small to be planets. We have one asteroid that is regarded as a dwarf planet, like the Ceres. It's actually in the asteroid belt, but it's big enough to be called a dwarf planet. How do asteroids orbit the sun? Look at where we find asteroids. So many debris, rock deposits. They are believed to be remains of particles that were left behind during the formation of our solar system, or better say during the formation of sun, particles that are left behind. Okay, while other particles were able to form the Earth, the planets, these ones are like the debris, the minor little fragments that are left behind. Okay, this region where we find them much is a region we call the asteroid belt. So if I'm to divide the solar system into parts, I can divide them into three parts. Take you back. They divide it into three parts. Here, the first part is the asteroid belt. So asteroid belt. The next part after Pluto is the Kuiper belt, and then the last part is the hot cloud. Okay, towards the edge of our solar system before you get to a different system altogether. Okay, now before this, we have these four planets. You can either call them the inner planets, the rocky planets. Okay, you call them the inner or rocky planets. While these ones are the Jovian planets or the outer planets. Okay, they are actually, some of them are gas giants, others are ice giants. Like the last two here is ice giants, and first two here after the belt, asteroid belt, is gas giants because they are composed more of gas, okay, than solid. Facts about solar system. Okay, we've seen the sun. These are facts about the sun. Facts about Mercury, the smallest planet. That is Mars. The diameter is about 4,808 kilometer. It's about 58 million kilometers from the sun. It takes just 88 days to travel around the sun. Okay, that is a year in Mercury. When we compare it to Earth, it's about 88 days in Earth. And it takes about 59 hours to spin around its axis. Okay, remember it takes 24 hours for Earth to spin around its axis. And this is the average temperature, 350 degree Celsius. Now, we have Venus. Venus is the slowest planet when it comes to moving around its um, axis. So that means for it to travel around its axis, it takes 243 hours. Think of it, 243 hours just to move around its axis. And for it to move around the sun, it's also very slow. It takes 200, but not as slow as when you compare to Earth. Okay, faster than Earth, 224 days. The average surface temperature is about 460 degrees, which is the hottest you can find as far as planet is concerned. Venus is the hottest known planet. Okay, the reason why it's hot is because of the concentration of greenhouse gases, carbon dioxide and sulfur there. The atmosphere is actually made up of carbon dioxide and sulfur. So most of the heat doesn't get to leave. Okay? The Earth is where we live. It takes 365 days to travel around the Earth. It takes 365 days for Earth to move around the Sun and 24 hours to move around its axis. The average temperature here is 20 degrees Celsius, and this is the diameter. Mass which is also known as the red planet, takes 24 hours, 37 minutes to move around its axis. Okay, almost similar to that of Earth, except for some few minutes. And it takes 687 days, approximately 2 years, to move around the sun. Okay, the average temperature is of minus 23 degree. Jupiter is the largest planet you can think of. The diameter is 142,600 kilometer. The distance from the sun is quite far, 778 million kilometer. It takes only 11.9, sorry, it takes not just only, it takes 11.9 years to move around the sun. This is actually because of the distance. Okay, the further you go, the further a planet is from the sun, the longer it takes to move around the sun. And it takes just 9 hours and 50 minutes to spin its axis, so it spins very fast. It means a day in Jupiter when compared with Earth is just 9 hours, 50 minutes. The average temperature is minus 120 degrees. The next is Saturn. Saturn is a planet with the greatest number of rings. Okay, but mind you, Jupiter has more moons than Saturn. But Saturn have more rings than Jupiter. So average surface temperature is minus 180. It takes just 10 hours, 40 minutes to spin around its axis. And to travel around the sun, it takes 29.5 years. And it's 120,200 kilometer in diameter. Okay. Then we have Uranus. Uranus is a planet, the only planet that spins, that is tilted at an angle different from others. It's like the north and the south is roughly, the northern hemisphere is roughly almost roughly becoming horizontal, right? It's roughly horizontal, not really horizontal, right? Okay, so it takes 10 hours 49 minutes for it to spin around its axis, and it's 4 years to travel, and it has few moons and few rings. Then Neptune, also ice giant like Uranus. Neptune has a lot of concentration of methane, okay, and some other gases like hydrogen, helium, and so on. It has a diameter of 50,000 kilometer, and it's 4,497 kilometer from the sun. It takes about 165 years to travel around the sun, and to spin around its axis, it takes 15 hours 48 minutes. Okay, for today's lesson, we are going to stop here and proceed to look at other things I talked about in the part 2 of Earth and beyond. So have a nice day, and uh, like my video or subscribe to my channel for more of this. And I'll need a lot of feedbacks from you guys. What I'm doing right, what I'm not doing right, please comment below to help me to know how to proceed. further. Okay, so in the next part 2 of this lesson and beyond, we're going to take the other parts of the lesson and also look at um, the different models or assumption of the Earth of the universe or solar system prior to this time. Okay, that's the heliocentric and geocentric model. So have a nice day. Have a nice time.